Mr. Antonucci here, and we're in section 9A, confidence intervals for the slope of a population regression line. So in this first video, we're going to describe the sampling distribution of the sample slope B. So when two quantitative variables x and y have a linear relationship, the least squares regression line, y hat equals a plus bx, is going to model that relationship. So if the data come from a random sample or randomized experiment, we may use a regression line to make inferences about the population regression line. In Unit 2, we interpreted y hat as the predicted value of y for a given x, and we can also view y hat as an estimator for the population mean at a given x. The population regression line then is written as mu of y equals alpha plus beta x. So here's the definition of the population regression line or sample regression line. It's calculated from every value. A regression line calculated for every value in the population is called a population regression line. The equation of the population regression line is mu sub y equals alpha plus beta x, where mu y is the mean y value for a given x value, alpha is the population y-intercept, and beta is the population slope. A regression line calculated from sample data is called a sample regression line. The equation of a sample regression line is y hat equals a plus bx, where y hat is the predicted y value or estimated mean y value for a given value of x, a is the y-intercept, and b is the sample slope. Now we have to be careful here because the symbols alpha and beta refer to the y-intercept and slope of the population regression line respectively. They are not the probabilities of type 1 and type 2 errors, which also are designated by the Greek letters alpha and beta. So you just have to be careful to pay attention to the context of how those variables are being used. So how does the slope of the regression line B compare to the slope of the population regression line beta? To check this out, we're going to examine the sampling distribution of the sample slope B. Inference about population slope beta requires the sampling distribution of B to be approximately normal. We'll cover the conditions in a bit, but for now, here are the formulas for its center and variability. The mean of the sampling distribution is B is the mean of B, which is beta, when the 10% condition, where n is less than 10% of the sample size, is met. The standard deviation of the sampling distribution of B is approximately standard deviation divided by standard deviation of x times square root n, where sigma is the population standard deviation of the residuals, and sigma sub x is the population standard deviation of the explanatory variable x. Now, I know that's a lot to take in, said a lot of words there. We're going to break it all down here in a minute. So a tip for you on the AP exam, the formulas for mean and standard deviation of the sampling distribution of B are going to be on that formula sheet for both sections. You just have to know how to use them and when to interpret them. So a couple facts before we jump into an example about the mean and standard deviation of sampling distribution of the sample slope B. Mu sub B represents the average sample slopes B across all possible samples of a given size. Since that equals beta, the sample slope B is an unbiased estimator of the population slope beta. Sigma sub B measures the typical difference between a sample slope B and the population slope beta. A larger sample size is going to reduce variability since n appears in the denominator of the sigma sub B. When the sampling with replacement, the standard deviation of B is given here. If observations aren't independent, the actual standard deviation is smaller, but when the sample is less than 10% of the population, this formula is still going to be accurate. So here's an example. For the population of 263 Old Faithful eruptions in a particular month, the population regression line is mu sub y equals 33.3 plus 13.3x. The standard deviation of residuals is 6.47 minutes, and the standard deviation of eruption duration is 1.18 minutes. Now imagine taking a random sample of 15 eruptions that occurred during this month and using the sample data to calculate B, which is the slope of the sample regression line for the predicting Y, which is equal to wait time until the next eruption in minutes, from X equals the duration of the previous eruption in minutes. So if we calculate and interpret the mean of the standard sampling distribution of B. So the mean sub B equals 13.3. If you selected all samples of 15 Old Faithful eruptions from this particular month and calculated the slope of the least squares regression line for predicting wait time until the next eruption in minutes from the duration of the previous eruption in minutes, for each sample, the sample slopes would have an average value of 13.3. Now, that is a very long interpretation of the mean of the sampling distribution, but that's in part due to the context of what we were talking about in this problem. Now we want to verify that the 10% condition is met, then calculate and interpret the standard deviation of the sampling distribution of B. Now, because 15 is less than 10% of the 263 eruptions in that month, we can calculate it and we get 1.42. Now, to interpret that, that means if you selected all possible samples of 15 Old Faithful eruptions from that particular month, calculated the slope of the least squares regression line for predicting wait time. For each sample, the sample slopes would typically vary from the population slope of 13.3 by about 1.42 minutes in this case. All right, guys, that's it for this one. Stay tuned for the next piece.